What if our solar system is boring? Tonight, we're going to explore 100 of the strangest planets ever discovered, scattered across our galaxy. You've probably seen artists' renditions of distant worlds in science documentaries. But here's what most people don't realize. The universe has created planets so bizarre, so impossible, that they challenge everything we thought we knew about how worlds can exist. Planets made of diamond, worlds where it rains glass sideways. Places where a year lasts just 16 hours. By the end of this journey, you're going to see our calm, predictable Earth as the cosmic anomaly it truly is. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This is going to be incredible. Take a moment to imagine something that shouldn't be possible. Picture a planet being squeezed like a cosmic lemon, its very shape warped by forces so extreme that it becomes an oval rather than a sphere. This isn't science fiction. This is PSR J-tooth 32 Tatunuas 5B, a world that exists 4,600 trillion miles from where you're sitting right now. The gravity of a dead star, what astronomers call a pulsar, has deformed this Jupiter-sized planet by 38%. Think about that for a moment. Imagine if Earth were suddenly stretched into the shape of an egg, the continents and oceans warping along impossible curves. That's the reality for this distant world, orbiting just 1 million miles from a stellar corpse that spins 300 times every second. But here's where it gets truly extraordinary. The atmosphere of this tortured planet is dominated by pure carbon and helium, creating clouds of soot that drift through an environment so hostile it defies comprehension. Under the crushing pressures within this world, that carbon doesn't remain as simple soot. It crystallizes into diamonds, literally. This is a planet that manufactures jewels in its atmospheric furnace, a cosmic jewelry box spinning through the void. The radiation from its pulsar companion would be instantly lethal to any form of life we can imagine, yet this world completes an entire orbit, its equivalent of a year, in just 7.75 hours. Not far away, astronomically speaking, lies another treasure that would make ancient kings weep with envy. At a distance of 240 trillion miles, in the constellation Cancer, orbits a world that may be composed largely of crystallized carbon. If 55 Cancri A, sometimes called Janssen, were truly made of diamond as scientists suspect, its value would exceed $26 non-illion. That's a number with 30 zeros after it. 384 million times the entire gross domestic product of Earth. This world, twice the size of our planet, races around its star in just 18 hours. The surface temperature reaches nearly 5,000 degrees Fahrenheit, hot enough to melt copper instantly. At those temperatures, carbon under extreme pressure forms diamonds throughout the planet's structure. Picture an entire world where the ground beneath your feet would be crystallized carbon, harder than any material in Earth's crust. But perhaps you're thinking these extremes are rare exceptions in our galaxy. Let me introduce you to WASP 76b, where the very concept of weather takes on meanings that would sound like fantasy if they weren't scientifically documented reality. On this world 3.9 trillion miles away in the constellation Pisces, iron doesn't exist as the solid metal you know. During the day, when temperatures soar to 4,300 degrees Fahrenheit, iron vaporizes completely. Massive winds, moving at thousands of miles per hour, carry this vaporized metal from the day side to the night side of the planet. There, in the relative coolness of eternal darkness, the iron vapor condenses and falls as rain. molten iron droplets falling from the sky like a metallic monsoon. This planet is nearly twice the size of Jupiter, yet its density is remarkably low due to the extreme heating from its nearby star. Scientists have detected something unprecedented in its metallic clouds. Concentric rainbows, or what they call glory phenomena. It's an optical effect never before witnessed beyond our own solar system, created by droplets of vaporized metal acting like prisms in an alien sky. If WASP-76b seems improbable, consider WASP-107b, a world that challenges our basic understanding of how planets can exist. This cosmic marshmallow has only 12% of Jupiter's mass, yet it's 94% of Jupiter's size. Its density is 8 times lower than water. This planet would literally float in Earth's oceans if you could somehow transport it here. Located 1.2 trillion miles from Earth, this super-puff planet is losing so much helium to space that it has created a tail of gas 5 times larger than the planet itself. Astronomers can see this tail of escaping atmosphere even before the planet itself comes into view. By all physical laws we understand, this world should have collapsed under its own gravity billions of years ago. Yet here it persists, maintained in its impossible state by tidal heating from its slightly elliptical orbit. A cosmic marshmallow that refuses to deflate. The universe, it seems, has a sense of poetry. At a distance of 1.5 trillion miles lies Kepler-16b, a world that would fulfill the dreams of anyone who ever watched a science fiction sunset. This planet orbits not one star, but 2. If you could stand on its surface, you would witness what the creators of Star Wars could only imagine. A double sunset, with one orange star and one red star sinking below the horizon together. Despite having 2 suns, this world remains bitterly cold, with temperatures ranging from -148 to -238 degrees Fahrenheit. Both of its stars are smaller and cooler than our Sun, and the planet orbits far enough away that even their combined energy cannot warm its surface. This world, 75% the size of Jupiter, maintains a stable orbit around its binary stellar system. A gravitational dance where 2 stars orbit each other every 41 days while the planet traces its own path around them both. The mathematics of such orbital mechanics are staggering in their complexity. Yet nature has found a way to make it work. At just 368 trillion miles away, practically next door in cosmic terms, lies HD 189733b, a world that appears as a brilliant blue jewel when viewed through our telescopes. From a distance, you might mistake it for another Earth, so vivid is its azure coloration. But this resemblance to our world is cruelly deceptive. The blue color comes not from vast oceans or a protective atmosphere, but from silicate particles suspended in winds that reach 8,700 miles per hour, 7 times faster than the speed of sound on Earth. These aren't particles of sand or dust as we know them. They're particles of glass forged in the planet's extreme atmosphere and hurled horizontally around the world in eternal storms of crystalline death. This was the first exoplanet to have its true color determined by astronomers, revealing a blue so intense it rivals our own Earth as seen from space. Yet, where our blue speaks of water and life, this blue speaks only of beauty wrapped in lethality. But if HD 189733b represents beauty hiding horror, then TRES-2b represents something even stranger, a world that seems to absorb the very concept of light itself. At a distance of 4.6 trillion miles, this planet absorbs 99% of all light that touches it. It reflects less light than charcoal, less than black paint, less than any material known to exist on Earth. This world, slightly larger than Jupiter, appears darker than the darkest night you've ever experienced. Yet, despite absorbing nearly all incoming light, it emits its own faint red glow from internal heat exceeding 1,800 degrees Fahrenheit. Picture a sphere of absolute blackness, hanging in space like a hole in the cosmos, emanating only the faintest ember-red glow. Scientists remain baffled by what atmospheric composition could create such perfect light absorption. No theoretical model can fully explain how a planet becomes this dark. It exists as a cosmic enigma, a world that seems to devour light itself. Yet perhaps the most extreme of all these impossible worlds is Kelt 9b, a planet that has become hotter than most stars. At 7,800 degrees Fahrenheit, this world exceeds the surface temperature of 70% of the red dwarf stars in our galaxy. During its day cycle, the heat is so intense that molecules themselves cease to exist. They break apart into individual atoms. Only during the planet's night, in the relative coolness of thousands of degrees, do these atoms recombine into molecules again. This world, located 4.1 trillion miles away, has been inflated to 1.65 times the size of Jupiter by the extreme heating from its blue-white star. It races around this stellar furnace in just 36 hours, so close that the very concept of a stable atmosphere becomes meaningless. And yet, even as we catalog these extremes, the universe presents us with GJ 436b, a world that defies physics in its own quiet way. This Neptune-like planet, a mere 196 trillion miles from Earth, is losing so much hydrogen that it has created a comet-like tail 2 million miles long, 50 times larger than the planet itself. But the truly impossible thing about this world is that it contains water ice at 570 degrees Fahrenheit. By every law of physics we understand, water should instantly vaporize at such temperatures. Yet here, under atmospheric pressure 20,000 times greater than Earth's, ice remains solid in conditions that should make it impossible. This world loses 1,000 tons of atmosphere every second, allowing astronomers to watch a planet literally dissolve before their eyes. Finally, at a distance of 8.7 trillion miles, we find WASP-12b, a world in the process of being consumed by its own star. The gravitational forces from its nearby sun have stretched this planet into an egg shape, 20% longer than it is wide. Its star is actively feeding on the planet, pulling away material in a process of cosmic cannibalism that will completely devour this world in just 10 million years. In cosmic terms, this planet has already received its death sentence, and we are witnessing its final moments played out across geological time. But as we contemplate these worlds caught in stellar death spirals, the universe reveals something perhaps even more poignant: planets that have been cast out entirely from their homes, wandering the cold darkness between stars like cosmic orphans. Imagine being 12 million years old in a universe that is nearly 14 billion years old. You're just 0.26% the age of Earth, a planetary infant by any measure. Yet unlike other young worlds, you drift alone through the vast emptiness between stars, with no sun to warm you, no stellar system to call home. This is the reality of PSO J318.522, floating in isolation 470 trillion miles from Earth. This orphaned world is 6 times more massive than Jupiter, still glowing with the residual heat of its own formation, like a slowly cooling ember in the cosmic dark. The warmth it carries is all it will ever have. There is no star to replenish this energy, only the gradual, inexorable cooling that will continue for billions of years until it becomes as cold as the void that surrounds it. Scientists can only speculate about the violent forces that ejected such a massive planet from its birth system. Perhaps it was a collision with another world, or maybe gravitational instabilities during the chaotic early stages of planetary formation. Whatever the cause, it was powerful enough to hurl a world 6 times Jupiter's mass completely out of its stellar neighborhood, condemning it to eternal wandering. The very fact that we can detect this orphan's faint glow speaks to the incredible sensitivity of our telescopes and the dedication of astronomers who search the darkness for these lost children of the cosmos. While some planets flee their stars, others press dangerously close, and WASP 103b represents the first world where we've actually observed a planet being physically reshaped by stellar gravity. Located 7.4 trillion miles away, this world has been stretched 7% in the direction of its star, transforming from a sphere into the shape of an American football. This planet, nearly 1.5 times the size of Jupiter, orbits so close to its star that its destruction is not a matter of if, but when. The same gravitational forces that stretch it into an oval will eventually tear it apart entirely. We are witnessing a world in its final millions of years, another cosmic death sentence, but this one written in the very shape of the planet itself. The detection of this deformation required the extreme precision of the Cheops Space Telescope, demonstrating how our technology continues to reveal details that were impossible to observe just decades ago. We are living in an age where we can literally watch planets change shape in real time. At a distance of just 258 trillion miles, relatively close in galactic terms, lies Upsilon Andromedae b, a world that showcases the most extreme climate differences imaginable. Between its day and night sides, there is a temperature variation of 2,556 degrees Fahrenheit, a greater difference than between ice and lava on Earth. The hot side reaches 2,552 degrees Fahrenheit, while the cold side drops to -4 degrees Fahrenheit. This world was one of the first exoplanets ever discovered, revolutionizing our understanding of worlds beyond our solar system when it was found in the constellation Andromeda. Its atmospheric winds desperately attempt to equalize these extreme temperatures, creating violent weather systems that rage across the planet but never succeed in stabilizing its climate. The physics of such extreme temperature gradients create perpetual atmospheric chaos, storms that would dwarf any hurricane Earth has ever seen, yet they can never bring thermal balance to this tortured world. If Upsilon Andromedae b challenges our understanding of planetary atmospheres, then WASP 193b challenges our understanding of matter itself. This giant world, located 7.4 trillion miles away in the constellation Draco, has a density 20 times lower than water. At 146 times the size of Jupiter, but containing only 14% of Jupiter's mass, this planet would literally float like cosmic cotton candy if you could somehow place it in a cosmic ocean. By every law of physics we understand, this world should not be able to maintain its inflated structure. It should have collapsed under its own gravity billions of years ago. Yet here it persists, held in its impossible state by some mechanism that continues to baffle astrophysicists. The planet exists in a state that seems to defy basic physical principles, a cosmic paradox floating through space. At 4.5 trillion miles distance, we encounter something unprecedented: the skeletal remains of what was once a gas giant. TOI 849b is the first planetary skeleton ever observed, the exposed rocky and metallic core of a world that has been completely stripped of its gaseous atmosphere. This planet, 3.4 times the size of Earth, is composed entirely of rock and metal with a density similar to titanium. It represents a frozen moment in planetary evolution, a snapshot of what remains when a gas giant is stripped bare by stellar winds or catastrophic events. Looking at this world is like examining the fossilized bones of a cosmic dinosaur, revealing the solid foundation that once supported a massive gaseous envelope. The survival of this core tells us about the incredible durability of planetary centers and the violent processes that can strip away thousands of miles of atmosphere while leaving the rocky heart intact. Perhaps nowhere is the alien nature of planetary weather more apparent than on K2 141b, a world one. 2 trillion miles away, that has created its own version of the water cycle. Except instead of water, it uses molten rock. This planet, slightly larger than Earth, maintains permanent oceans of lava at temperatures reaching 5,400 degrees Fahrenheit. On this world, rocks evaporate into the atmosphere, form clouds of vaporized stone, and then rain back down as liquid rock. The winds that drive this rocky weather system reach speeds of 3,100 miles per hour. Imagine hurricanes carrying not water droplets, but vaporized mountains through the air. The planet maintains a surface of permanently molten stone, as if our own oceans were replaced by liquid granite, flowing in vast, glowing seas. In the depths of our galaxy, 80.7 trillion miles from the galactic center, drifts another orphaned world, but this one is smaller than Earth itself. Ogle 2016 BLG 1928 has only 75% of Earth's size and 30% of its mass, making it the smallest rogue planet ever detected. This tiny world was discovered only by chance, when it passed directly between Earth and a distant star, bending the star's light gravitationally in a phenomenon called microlensing. Finding this planet was like discovering a grain of sand in an ocean by the shadow it cast on a lighthouse beam millions of miles away. At -400 degrees Fahrenheit in the interstellar void, this small world represents the ultimate lonely fate of planets ejected from their systems. Too small to retain any significant heat, too far from any star to receive warmth, condemned to drift in absolute cold and darkness for billions of years. Yet even in this catalog of extremes, HAT P7b stands out for its ethereal beauty. Located 6.4 trillion miles away, this world's clouds are composed of aluminum oxide, the same material that forms rubies and sapphires here on Earth. As these mineral clouds move across the planet's surface, they create a shifting, sparkling display that changes the world's brightness by 15%. This planet, 1.4 times the size of Jupiter, was the first exoplanet to have its cloud patterns mapped in detail, revealing weather systems made of materials we consider precious gems. Imagine clouds of crystalline sapphire drifting through alien skies, catching and reflecting starlight in patterns that shift like cosmic jewelry floating through the atmosphere. At a distance of 5.2 trillion miles, WASP 121b presents us with perhaps the most dramatic example of atmospheric escape ever observed. This world, 1.65 times larger than Jupiter, is losing trillions of pounds of atmosphere every second. Iron and magnesium float vaporized in its upper atmosphere like metallic blood coursing through atmospheric veins. The gravitational pull from its nearby star has stretched this planet into a teardrop shape, like a drop of cosmic rain perpetually on the verge of falling. The escaping atmosphere streams away from the planet in a tail of hot gas, creating a comet-like trail of planetary material fleeing into space. We are watching a world literally evaporating before our eyes, its very substance bleeding away into the cosmic void. Finally, at a distance of 3.6 trillion miles, we find TOI 3757b, a world that shouldn't exist according to everything we thought we knew about planetary formation. This planet, 1.35 times larger than Jupiter, orbits a red dwarf star. The problem is that red dwarfs, theoretically, cannot form gas giants of this size. With a density 4 times lower than water, this world defies not only our theories of how planets form around small stars, but also our understanding of how such low-density worlds can maintain their structure in the hostile radiation environment around red dwarfs. Its very existence forced scientists to revise fundamental models about planetary formation, proving once again that the cosmos always has surprises that confound our most carefully constructed theories. This impossible world floating around its small red star reminds us that for all our knowledge, for all our sophisticated models and precise measurements, the universe continues to create phenomena that exceed our understanding and challenge our assumptions about what is possible in the vast theater of space. As we venture deeper into this cosmic menagerie, we encounter worlds where the very concept of a habitable zone becomes a cruel deception. Consider Kepler 438b, a world that sits 9 trillion miles from Earth, tantalizing close to our own planet's size at 1.2 times Earth's dimensions. At first glance, you might think this world represents hope. It orbits at precisely the right distance from its star for liquid water to exist on its surface. But this hope dissolves under closer examination. The planet receives a bombardment of radiation 640 times more intense than anything Earth experiences. Its red dwarf star unleashes X-ray flares of extraordinary violence every 100 days. Events so powerful that if they occurred near Earth, they would instantly collapse our entire technological civilization, frying satellites, destroying power grids, and rendering electronics useless across the globe. This world sits in what astronomers call a false habitable zone, technically in the right position for liquid water, but bathed in such lethal radiation that any life as we know it would be sterilized within moments of exposure. It serves as a sobering reminder that the universe can create the perfect conditions for life while simultaneously making life absolutely impossible. At a distance of 8 trillion miles, we find WASP-17b, a world that defies one of the most fundamental expectations about planetary motion. While virtually every planet we know orbits in the same direction as its star's rotation, WASP-17b moves backward. It's what astronomers call a retrograde orbit, spinning against the cosmic grain. This giant world, nearly twice the size of Jupiter, has a density 17 times lower than water, making it so fragile that any significant gravitational disturbance could tear it apart like a cosmic soap bubble. Its backward motion tells a story of violence, perhaps a collision with another planet, or a close gravitational encounter with a passing giant that flung it into its current rebellious orbit. The very existence of this gossamer world spinning the wrong way around its star speaks to the chaotic and violent history of planetary systems where worlds can be hurled into impossible configurations by forces beyond our everyday comprehension. 3 trillion miles away lies CoRoT 7b, a world that holds a special place in astronomical history as the first rocky super-Earth ever discovered in transit across its star. This planet, 1.63 times larger than Earth, opened an entirely new category of worlds, rocky planets larger than Earth but smaller than Neptune. But this historical significance comes with a hellish reality. The planet's day side maintains a surface temperature of 4,500 degrees Fahrenheit, hot enough to keep rock in a permanently molten state. Here, it literally rains rocks, Silicate materials vaporize in the extreme heat, rise into the atmosphere, and then condense and fall back to the surface as solid stone droplets. Imagine standing on a world where instead of water falling from the sky, chunks of vaporized rock precipitate from clouds of stone vapor, striking a surface that flows like an ocean of molten granite. Half of this planet exists in a state of perpetual geological liquefaction. Yet even Corot 7b's extreme proximity to its star pales compared to Kepler 78b, located 2.5 trillion miles from Earth. This world, just one. 24 times the size of Earth, orbits so close to its star that it completes an entire year in just 8.5 hours. Think about that for a moment. On this world, you could watch the sun rise and set nearly 3 times in a single Earth day. By every theory of planetary formation we understand, this world should not exist. It orbits so close to its star that during the early phases of stellar development, when the star was larger and more active, the planet should have been completely vaporized. Yet here it persists, a rocky world racing around its star at such incredible speed that it challenges the fundamental limits of how close a planet can orbit without being torn apart by tidal forces. Scientists call this world the planet that shouldn't exist, and its continued presence forces us to reconsider basic assumptions about how rocky worlds form and survive in the most extreme stellar environments. At just 2 trillion miles away lies WASP-UIS 18b, a world so massive it represents something between a planet and a failed star. With 10 times the mass of Jupiter compressed into a volume only slightly larger than Jupiter itself, this monster contains the mass of 3,180 Earths in a space that seems impossibly compact. This world is so massive that it actually deforms its host star, creating visible bulges in the stellar surface through sheer gravitational influence. The planet exists right at the boundary between what we consider a planet and what we call a brown dwarf. A failed star that never quite accumulated enough mass to ignite nuclear fusion. But perhaps most remarkably, this giant's extreme proximity to its star is actually accelerating the star's evolution. The gravitational interaction generates tidal heating within the star itself, potentially shortening the stellar lifetime and fundamentally altering the star's development. We are witnessing a planet so massive it can change the very fate of the star it orbits. Just 240 trillion miles away, in a system we've encountered before, lies 55 Cancri F, a Neptune-like world with one of the most eccentric orbits known. During its 260-day year, this planet's distance from its star varies by 50%, creating the most extreme seasonal variations imaginable. What makes this world particularly intriguing is that during part of its highly elliptical orbit, it actually passes through what would normally be considered the habitable zone, that region where liquid water could theoretically exist. For a brief portion of each orbit, this world experiences what we might call a habitable summer, though whether any moon or captured object could maintain stable conditions during these fleeting warm periods remains an open question. The planet's temperature swings are dictated not by axial tilt, like Earth's seasons, but by the dramatic changes in stellar heating as it swings from the outer reaches of the system to dangerously close proximity to its star. Perhaps no world demonstrates orbital extremes quite like HD 80606b, located 1.2 trillion miles away. This giant, 4 times more massive than Jupiter, follows an orbit so elliptical that its distance from its star varies by a factor of 30 during each orbit. At its farthest point, it receives no more heating than Jupiter gets from our Sun. At its closest approach, it receives 800 times more energy than Earth. During the closest approach to its star, what astronomers call periasteron, this world heats up by 1,160 degrees Fahrenheit in just 6 hours. Imagine the thermal shock of a planet-sized object being thrust into a stellar furnace and then yanked back out into the cold within the span of a single day. The temperature oscillates between 200 degrees Fahrenheit at its farthest point to 2,700 degrees Fahrenheit during closest approach over the course of its 111-day orbit. The atmospheric dynamics on such a world would be incomprehensible. Massive global storms triggered by thermal expansion and contraction, weather patterns that rebuild themselves from scratch multiple times each year as the planet undergoes its extreme thermal cycling. At 8 trillion miles distance, WASP-79b presents us with something unprecedented, a giant planet with a completely transparent atmosphere. This world, 1.59 times larger than Jupiter, has 0 detectable clouds at any altitude, creating a crystalline atmospheric window that allows us to observe 620 miles deep into the planet's gaseous envelope. For atmospheric scientists, this planet represents an extraordinary laboratory. Most gas giants hide their internal structure beneath layers of opaque clouds, but WASP-79b offers an unobstructed view into the chemical composition and structure of a giant planet's atmosphere. It's as if the universe provided us with a glass-walled terrarium containing a Jupiter-sized world, allowing us to study atmospheric layers that are normally hidden from view. Nearly 6 trillion miles away drifts HAT P32b, another world that seems to mock our understanding of planetary physics. This giant, 1.89 times larger than Jupiter, has exactly the same density as expanded polystyrene foam. It would literally float on water if you could find an ocean large enough to contain it. With less than 1 Jupiter mass spread across a volume much larger than Jupiter itself, this world maintains an atmospheric envelope nearly 37,000 miles thick through constant heating from its nearby star. The planet exists like a perpetually inflated cosmic balloon held in its impossible state of expansion by the continuous energy input from stellar radiation. Finally, at a distance of 12.3 trillion miles, we encounter TIC 24012495-B, a world that experiences the most extreme orbital variations known to science during its 69. 7-day orbit. This planet's distance from its star varies by a factor of 6, swinging from 10 times closer than Mercury is to our Sun, out to approximately Earth's distance from the Sun. As it travels this cosmic roller coaster, the planet's speed varies from 33,000 miles per hour to 190,000 miles per hour. Velocity changes that would subject any hypothetical astronauts to gravitational forces that would render them unconscious. The temperature swings from negative 112 degrees Fahrenheit at its farthest point to 1,402 degrees Fahrenheit during closest approach. This world experiences the most dramatic climate changes of any known planet, with thermal variations more extreme than the difference between an Arctic winter and the surface of Venus, all compressed into a cycle that repeats 3 times each Earth year. As we continue our journey through these impossible worlds, we encounter phenomena that push the boundaries of what we consider physically possible. At a distance of 3.4 trillion miles lies Kepler-10b, a world that is quite literally evaporating before our eyes. This planet, 1.5 times the size of Earth, trails behind it a tail of vaporized rock stretching 124,000 miles into space, longer than the distance from Earth to the Moon. This world has the same density as pure metallic nickel composed of 90% iron and heavy metals. Imagine a cannonball the size of a planet racing through space while being slowly dissolved by its star's relentless energy. The temperatures are so extreme that solid rock vaporizes into silicate gas, which is then stripped away by stellar winds to form this ghostly tail of planetary material. We are witnessing planetary destruction in real time. Astronomers can actually observe this world losing mass as it orbits, watching through telescopes as a planet slowly disintegrates, atom by atom, into the cosmic void. The process is inexorable. This world is being consumed not by collision or catastrophe, but by the gentle, persistent erosion of stellar energy turning solid matter into vapor. At 2.3 trillion miles away we find WASP-33b, a world caught in one of the strangest dances in the cosmos. This planet, twice the size of Jupiter, orbits a star that pulses like a cosmic heartbeat every 2.5 hours. The star itself expands and contracts rhythmically, and remarkably, the planet's temperature oscillates in perfect synchronization with these stellar pulsations. Picture a world that literally breathes with its star, growing hotter and cooler in rhythm with the expansion and contraction of its stellar companion. But this synchronized dance has an additional twist. The planet orbits backward, moving in the opposite direction to its star's rotation. It's as if the cosmic partners are waltzing together while spinning in opposite directions, creating a celestial choreography of extraordinary complexity and beauty. Some worlds challenge not just our understanding of physics, but our very definitions of what constitutes a planet. XO3b, located 2 trillion miles away, exists in the gray area between planet and failed star. With 12 times the mass of Jupiter, this object may actually be burning deuterium in its core, a nuclear process that would technically make it a brown dwarf rather than a true planet. This world is twice as dense as Jupiter, despite being only 15% larger, suggesting an internal structure fundamentally different from normal gas giants. It represents an identity crisis on a cosmic scale. An object that might be the smallest possible star masquerading as the largest possible planet. The very fact that we struggle to classify it reminds us that the universe doesn't always fit neatly into our human categories. Perhaps no world better demonstrates the extremes of planetary composition than HD 149026b, a gas giant with an impossible secret. Located 1.5 trillion miles away, 70% of this planet's mass consists of its solid core, a proportion that should be impossible for a gas giant. That core contains the equivalent mass of 80 Earths, compressed into solid rock and metal. Most gas giants have small, rocky cores surrounded by vast envelopes of gas. But this world inverts that expectation, creating what is essentially a super-Earth wrapped in a relatively thin gaseous atmosphere. It's the densest planet known to science, challenging every model we have for how gas giants form and evolve. At an incredible distance of 26.9 trillion miles lies CoRo T14b, a world with the density of carbon steel. Standing on its surface, you would weigh 4.6 times more than you do on Earth. A 150-pound person would suddenly weigh 710 pounds and would struggle to move under the crushing gravitational pull. This planet is composed of 85% rock and heavy metals, making it more like a gigantic cannonball than a traditional gas giant. The surface gravity would be so intense that it would fundamentally alter how any atmosphere behaves, creating pressure gradients and weather patterns unlike anything we see on less massive worlds. In contrast to these dense, heavy worlds, Kepler 7b represents a milestone in our understanding of planetary atmospheres. Located 18.5 trillion miles away, this was the first exoplanet to have its cloud patterns mapped in detail, inaugurating a new era in extraterrestrial meteorology. Only 50% of this planet is covered by reflective clouds, creating an asymmetric weather pattern that changes as the planet rotates. Its low density makes it an ideal laboratory for studying atmospheric dynamics on a planetary scale, allowing scientists to observe how weather systems develop and evolve on a world with fundamentally different properties from Earth. At 2.7 trillion miles distance, HAT P2b presents us with yet another massive giant. 8 times Jupiter's mass concentrated into a volume only 20% larger than Jupiter. This world follows a significantly elongated orbit, creating extreme thermal variations as it swings closer and farther from its star. The gravitational influence of this massive planet likely affects the entire architecture of its stellar system. With the equivalent mass of 2,528 Earths, it has enough gravitational pull to potentially alter the orbits of any other planets that might exist in the system, acting like a cosmic puppeteer controlling the movements of smaller worlds. Just 1.8 trillion miles away lies WASP-8b, a world that combines 2 rare orbital characteristics. It moves backward around its star, while also following an elliptical path. This double rarity suggests a violent history involving close gravitational encounters with other massive objects that fundamentally altered its orbital trajectory. The combination of retrograde motion and elliptical orbit creates a unique heating pattern where the planet experiences seasons dictated not by axial tilt, but by complex orbital mechanics. The thermal and gravitational stresses from this configuration would create atmospheric dynamics unlike anything seen on planets with more conventional orbits. Remarkably close to us, at just 187 trillion miles away, we find AU Microscopy b, a world that proves planets can survive in the most hostile stellar environments imaginable. This planet, 4 times larger than Earth, orbits a star that unleashes flares 100 times more powerful than anything our Sun produces. The system is only 22 million years old, barely out of cosmic infancy, and the star is still going through the hyperactive phase of stellar youth. Despite constant bombardment by radiation and charged particles that would strip away most atmospheric envelopes, this planet maintains its gaseous atmosphere, suggesting either powerful atmospheric replenishment mechanisms or an extraordinarily strong magnetic field that deflects the stellar assault. Finally, at a distance of 196 trillion miles, we encounter Gliese 436b, a world that hosts one of the most exotic states of matter in the known universe. This Neptune-like planet contains solid ice at temperatures of 570 degrees Fahrenheit. A physical impossibility under normal conditions. The ice remains frozen not because of cold temperatures, but because of atmospheric pressure 20,000 times greater than Earth's surface pressure. Under such extreme compression, water molecules are forced into a solid crystalline structure despite temperatures that would normally vaporize them instantly. It's a demonstration of physics so extreme that we have no equivalent on Earth. But this world's impossibilities don't end with hot ice. It's also losing so much hydrogen to space that it has created a comet-like tail 50 times larger than the planet itself. A ghostly streamer of escaping gas that extends millions of miles behind the planet as it orbits. We can literally see this world's atmosphere bleeding away into space, creating a visible trail of planetary material fleeing into the cosmic void. In the grand theater of cosmic extremes, some worlds showcase not destruction, but the extraordinary power of atmospheric dynamics to create order from chaos. WASP 43b, located 6 trillion miles away, demonstrates how violent winds can paradoxically create perfect thermal equilibrium across an entire planet. This world, similar in size to Jupiter, experiences atmospheric convection so intense that it acts like a cosmic blender, mixing the entire gaseous envelope with unprecedented efficiency. The winds are so powerful that they completely eliminate any temperature difference between the day and night hemispheres, creating what amounts to a planetary air conditioning system that maintains uniform temperatures across the entire world. Think about this for a moment. On Earth, our day and night sides can differ by dozens of degrees, even with our relatively mild atmospheric circulation. But on WASP 43b, the atmospheric mixing is so thorough that the planet maintains thermal homogeneity across its entire surface. It's a perfect example of how extreme atmospheric dynamics can create unexpected stability and uniformity on a planetary scale. Perhaps nowhere in the known universe do we find a more dramatic example of cosmic choreography than in the Kepler-36 system, located 7.4 trillion miles away. Here, two worlds, one 1.5 times Earth size and another 3.7 times larger, perform a gravitational dance so close that each planet would appear 5 times larger than our Moon when viewed from the surface of the other. These cosmic twins approach to within just 1.2 million miles of each other, only 5 times the distance between Earth and our Moon. During their closest approaches, an observer on one world would watch the other planet grow dramatically in the sky, becoming a looming presence that would create spectacular eclipses and generate tidal forces far more extreme than anything we experience from our own Moon. The gravitational interaction between these worlds creates a synchronized orbital dance, where each planet's gravity influences the other's path through space. Picture standing on one of these worlds during close approach. The other planet would fill a significant portion of the sky, its surface features visible to the naked eye, its gravity creating tides in any oceans that might exist. At a distance of 246 trillion miles lies HD 4311G, a world that represents one of the cruelest deceptions in the cosmic catalog. This super-Earth, 2.3 times larger than our planet, sits precisely in the habitable zone, the region where liquid water should be able to exist on a planet's surface. But this perfect positioning is rendered meaningless by the violent nature of its star. The stellar radiation is so intense that any water that might have once existed on this world was vaporized and stripped away billions of years ago. X-ray bombardment from the star creates conditions utterly hostile to any form of life we can imagine. This world serves as a sobering reminder that being in the habitable zone is just the first requirement for a world to potentially support life. Stellar activity, atmospheric composition, magnetic field strength, and countless other factors must align to create truly habitable conditions. At 4 trillion miles distance, we encounter WASP 6b, a world distinguished by its extraordinary atmospheric chemistry. This planet, 1.2 times larger than Jupiter, has an atmosphere so saturated with sodium that it creates a unique spectral signature unlike any other known world. The abundance of sodium gives this planet a distinctive yellowish glow, as if it were permanently illuminated by giant urban streetlights. The concentration is so high that it fundamentally alters how we observe the planet's light spectrum, creating an unmistakable fingerprint in the cosmic catalog. Scientists remain puzzled by what process could concentrate sodium to such extreme levels in a planetary atmosphere. Some unknown chemical or physical mechanism is actively accumulating this specific element, creating atmospheric conditions that exist nowhere else in our current observations of the cosmos. Nearly 6 trillion miles away orbits Kourou T2b, a world bombarded by X-ray radiation 10,000 times more intense than anything Earth receives. This planet, 1.5 times larger than Jupiter, circles a young star only 100 million years old, still in the hyperactive phase of stellar youth when radiation output can be extraordinarily violent. The bombardment is so intense that scientists can actually measure changes in the planet's atmospheric structure over just a few years of observation. We are witnessing atmospheric erosion happening on human timescales, watching as stellar energy strips away layers of planetary atmosphere in real time. Any life as we know it would be sterilized instantly in such an environment, yet the planet persists, slowly shrinking as its outer layers are boiled away by the relentless stellar assault. Perhaps no world better demonstrates the extreme limits of planetary inflation than TRES-4b, located 8.6 trillion miles away. This giant planet, 1.8 times larger than Jupiter, has a density lower than cork. It would literally float on water if you could find an ocean large enough. The stellar heating has expanded this world's atmosphere so dramatically that it has become barely more substantial than a cosmic soap bubble. The planet represents the most extreme example known of stellar energy overcoming planetary gravity in determining a world's final size and structure. This delicate giant barely maintains gravitational cohesion. Any significant gravitational disturbance could potentially tear it apart, dissolving it into a cloud of dispersed gas. Yet it continues to orbit its star, a testament to the delicate balance between expansion and gravitational binding that allows such gossamer worlds to exist. At 5.9 trillion miles distance lies WASP-15b, one of the rarest orbital configurations known to astronomy. This planet, 1.4 times larger than Jupiter, follows a polar orbit, passing over the north and south poles of its star rather than circling around its equator. Less than 1% of all known exoplanets have such polar orbits, making this world truly exceptional. The process that could create such an unusual orbital configuration remains a mystery to scientists. It would require extreme gravitational perturbations or catastrophic events during the system's formation to knock a planet into such an unlikely trajectory. This world's unique perspective on its star creates conditions unlike any other planet we know. It experiences the stellar poles rather than the equatorial regions, receiving different patterns of radiation and magnetic field exposure. At an immense distance of 17.4 trillion miles, we find Kepler-432b, a world living under a cosmic death sentence. This planet, 1.3 times larger than Jupiter, orbits a star that has already begun its evolution into a red giant phase. The stellar expansion has already commenced, giving this planet only a few million more years before it will be completely engulfed and vaporized. We are witnessing the final chapter in this world's existence, a slow-motion catastrophe played out over geological time. This system offers scientists a unique opportunity to observe how planets are affected by stellar evolution, watching in real time as a star gradually heats and ultimately destroys its planetary companions. Nearly 4 trillion miles away spins Hat P41b, a world subjected to one of the most chaotic stellar environments imaginable. This planet, 1.2 times larger than Jupiter, orbits a star that completes a full rotation in just 2.7 days, creating a stellar magnetic field that changes unpredictably on timescales of hours. The ultra-rapid stellar rotation generates a chaotic magnetic environment that bombards the planet with charged particles in completely unpredictable patterns. The planet receives variable energy as different active regions of the rapidly spinning star pass by, creating atmospheric conditions that fluctuate dramatically over periods of just days. This world exists in a constant state of magnetic chaos, buffeted by stellar winds and radiation that vary on timescales far shorter than any stable climate system could adapt to. Finally, at 4.9 trillion miles away, we encounter WASP-70b, a world that presents us with a meteorological paradox. This planet, 1.5 times larger than Jupiter, has an atmosphere rich in water vapor, yet mysteriously forms no visible clouds whatsoever. Despite abundant atmospheric moisture, the planet maintains complete transparency, no haze, no obstruction, no condensation that we can detect. The atmospheric conditions somehow prevent water vapor from condensing into droplets, maintaining the humidity in a permanently gaseous state that remains crystal clear. This phenomenon represents a type of atmospheric chemistry we've never encountered before, where abundant water remains invisible in the planet's transparent gaseous envelope, creating weather patterns governed by physical principles we don't yet fully understand. Among all the impossible worlds we've encountered, perhaps none represent the ultimate test of planetary survival, quite like Kepler-70b and Kepler-70c. These two small worlds, located 7 trillion miles away, have literally been through stellar hell and emerged on the other side. These planets, smaller than Earth with radii of just 1,200 and 1,300 miles respectively, actually passed through the interior of a red giant star when their host star expanded during its death throes. Think about that for a moment. These worlds were completely engulfed by stellar material, traveling through the actual interior of a star for millions of years. When the star finally shed its outer layers and contracted into a white dwarf, these planetary cores emerged like cosmic phoenixes, reborn from stellar ashes. They represent the ultimate proof that rocky planetary cores can survive the most extreme conditions imaginable in the universe. Standing on the surface of either world today, you would be on ground that has literally traveled through the heart of a star. At a distance of 4 trillion miles lies Qatar 1b, a world that tells us about the fundamental role of stellar metallicity in planetary formation. This planet, 1.2 times larger than Jupiter, formed around a star containing 3 times more heavy elements than our Sun. This chemical abundance is reflected throughout the planet's composition, creating atmospheric chemistry fundamentally different from what we see in planets that formed around metal-poor stars. The world serves as a natural laboratory for understanding how the presence of heavy elements in the original stellar disk affects the final composition and characteristics of the planets that form. The chemical richness inherited from its stellar parent has created a world with atmospheric properties that challenge our standard models of planetary atmospheres, showing us how elemental abundance in the birth environment shapes the final character of the worlds that emerge. Located 4 trillion miles away, WASP-31b offers us something unprecedented, a completely transparent window into the internal structure of a gas giant. This planet, 1.5 times larger than Jupiter, has an atmosphere so clear that we can observe atmospheric layers that are normally hidden beneath opaque clouds. Different chemical layers within the atmosphere are clearly distinguishable, like looking through a glass window into the complex interior structure of a giant gaseous world. For atmospheric scientists, this represents an ideal natural laboratory. A chance to study the internal dynamics and chemical stratification of a gas giant without the interference of clouds or atmospheric haze. The transparency extends through over 620 miles of atmospheric depth, revealing details of atmospheric composition and circulation patterns that remain hidden on virtually every other gas giant we've observed. At 15, 4 trillion miles distance lies CoRoT 1b, a world with profound historical significance in the study of exoplanets. This planet, 1.5 times larger than Jupiter, was the first discovery of the CoRoT space mission, and it immediately challenged every theoretical prediction scientists had made about how such worlds should appear. The planet proved to be much less dense than existing models predicted, forcing a complete revision of planetary formation theories that were considered well established at the time of its discovery. This world represents a pivotal moment in exoplanet science, the point where observational data began to consistently outpace theoretical predictions. CoRoT 1b inaugurated an era where empirical discoveries guide the development of new theoretical models, rather than observations simply confirming existing theories. It marked the transition from a field where we thought we understood planetary formation to one where we realized the universe was far more creative than our models had imagined. Just 4.3 trillion miles away orbits WASP-39b, which has become one of the most intensively studied exoplanets in history. This world, 3 times larger than Jupiter, contains one of the highest concentrations of atmospheric water vapor ever detected in an exoplanet. The planet's atmosphere is organized in distinct layers of clouds at specific altitudes, creating a complex, three-dimensional structure that provides ideal conditions for studying planetary atmospheric dynamics. Different types of clouds form at different heights, creating a stratified atmosphere that varies dramatically with altitude. This world has become the standard reference point for atmospheric studies of exoplanets, providing baseline data that scientists use to understand and interpret observations of other similar worlds. Its well-characterized atmosphere serves as a cosmic textbook for understanding how gas giant atmospheres function. At 14.2 trillion miles away, we encounter Kepler 413b, a world caught in a perpetual state of climatic chaos. This planet, 4 times larger than Earth, has a rotational axis that wobbles 30 degrees every 11 years. Imagine if Earth's seasons changed not just annually but also underwent dramatic shifts in intensity over decade-long cycles. The extreme axial wobble creates completely unpredictable climate variations. Seasons vary dramatically in intensity and duration as the planet's orientation shifts, making any stable climate patterns impossible. The cause of this wobbling motion is a nearby binary star system whose gravitational influence constantly perturbs the planet's rotation. This gravitational interference creates a world where weather patterns and seasonal cycles are perpetually chaotic, with no stable climate state ever achievable. Any life that might evolve on such a world would need to be extraordinarily adaptable to survive in an environment where the basic parameters of climate change unpredictably over timescales of just a few years. Perhaps no world holds a more special place in the history of exoplanet atmospheric science than HD 29458b, known as Osiris, located just 983 trillion miles away. This planet was the first exoplanet to have its atmosphere chemically analyzed, launching the entire field of exoplanet atmospheric characterization. This world was also the first planet where we detected atmospheric escape in real time. Scientists observed a tail of hydrogen gas stretching 124,000 miles behind the planet as it orbits. The planet loses an astounding 10,000 tons of hydrogen every single second, creating a visible stream of escaping atmosphere that we can observe with telescopes. This ongoing atmospheric hemorrhaging provided the first direct evidence that planets can literally evaporate, losing substantial portions of their atmospheric envelopes to space over cosmic time. Watching Osiris is like observing planetary destruction in slow motion. A world slowly dissolving into the cosmic void, one molecule at a time. At 5.5 trillion miles away lies WASP-P4b, a planet providing us with perhaps the most precise measurement of planetary death ever obtained. This world, 1.4 times larger than Jupiter, has an orbit that is measurably decaying. Its orbital period decreases by 0.075 seconds every year due to tidal friction with its star. Scientists have calculated that this planet will be completely engulfed by its star in exactly 40 million years. We are witnessing planetary death in extraordinary slow motion, able to measure the gradual spiral toward destruction with telescopic precision. This world offers a unique laboratory for studying tidal physics on a planetary scale, allowing scientists to measure how orbital energy converts to heat through gravitational deformation, ultimately leading to the planet's inevitable destruction. Located 7.4 trillion miles away, Kepler 62f represents one of the most tantalizing possibilities for life beyond Earth. This world, 1.4 times larger than our planet, is likely a global ocean world. A planet with no continents, covered entirely by deep oceans. The planet sits at the perfect distance from its star to maintain permanent liquid water oceans, and it has sufficient atmospheric greenhouse effect to keep those oceans from freezing, even though it receives less stellar energy than Earth. This creates stable conditions that could potentially support life for billions of years. The prospect of a world covered entirely by warm oceans with no land masses to interrupt the global circulation patterns creates the possibility of ocean currents and climate systems unlike anything on Earth. Such a world might harbor forms of life adapted to purely aquatic environments spanning an entire planet. Finally, at 2.8 trillion miles distance, we find HAT-P1b, a world of historical significance as one of the first hot Jupiters ever discovered. This planet, 4 times larger than Jupiter, helped establish an entirely new category of planets that challenged our understanding of planetary system architecture. The discovery that giant planets could exist so close to their stars, much closer than any planet in our solar system, revolutionized our understanding of how planetary systems form and evolve. This world proved that planetary migration was not just possible, but common, with gas giants spiraling inward from their cold birthplaces to orbit scorchingly close to their stars. HAT-P1b's unexpectedly low density helped establish the concept of thermally inflated planets, where intense stellar heating expands planetary atmospheres far beyond their normal size, creating gossamer worlds that barely maintain gravitational coherence while orbiting in the blazing heat of their nearby stars. As we venture deeper into this cosmic catalog, we encounter worlds that push the very limits of orbital mechanics. WASP-19b, located 5 trillion miles away, holds the record as one of the fastest orbiting planets known to science. This world, 1.4 times larger than Jupiter, completes an entire orbit around its star in just 18.9 hours. To appreciate this speed, consider that this planet travels at 139,000 miles per hour around its star. Fast enough to circle Earth's equator in just 3 minutes if it could somehow travel in a straight line. The planet orbits 7.2 times closer to its star than Mercury does to our Sun, experiencing gravitational and thermal forces that strain the very limits of what a planet can endure while remaining intact. At such extreme proximity, the planet experiences tidal forces that would tear apart any world not held together by enormous gravitational self-attraction. The speed of its orbit creates a year shorter than many Earth days, a world where stellar sunrises and sunsets would flash by in a blur of light and shadow. Standing on this world, if such a thing were possible, you would witness the star racing across the sky at impossible speeds, completing its celestial journey in less than a single Earth day. At 9.2 trillion miles away lies Kouroti 9b, a world that represents a rare middle ground in the spectrum of planetary temperatures. This planet was the first temperate world ever discovered transiting its star, opening an entirely new observational category for astronomers. With surface temperatures similar to Mercury despite its 95-day orbital period, this world occupies a fascinating intermediate position. Neither the scorching hot Jupiters that orbit extremely close to their stars, nor the frigid gas giants that circle in the outer reaches of their systems. Such temperate worlds are observationally rare because few planets with moderate temperatures happen to pass directly in front of their stars from our perspective. This rarity makes every discovery like Kouroti 9b extraordinarily valuable scientifically, offering insights into planetary atmospheres under conditions that bridge the gap between extreme heat and extreme cold. The planet represents a cosmic middle ground that helps scientists understand the full spectrum of possible planetary environments. Perhaps no world better embodies the possibility of life beyond Earth than Kepler-22b, located 3.8 trillion miles away in what astronomers call the Goldilocks zone, the perfect distance for liquid water to exist. This world, 2.4 times larger than Earth, orbits a star remarkably similar to our own Sun. The planet receives just enough stellar energy to maintain global oceans at comfortable temperatures, making it one of the most promising candidates in the search for extraterrestrial life. Its host star shares so many characteristics with the Sun that this system essentially represents a scaled-up version of our own solar system. Standing on this world, if it has a solid surface beneath potential oceans, you might look up at a sun very much like the one that warms Earth, in a sky that could be filled with water vapor clouds, drifting over global seas that have remained liquid for billions of years. The familiarity of its stellar environment makes this world feel almost like a cosmic cousin to Earth, a place where the conditions that allowed life to flourish on our planet might be replicated on a larger scale. At 5 trillion miles distance, we find WASP-34b, a world caught in the midst of stellar evolution. This planet, 1.2 times larger than Jupiter, orbits a star that is leaving the stable main sequence phase and beginning to expand into a red giant. As the star evolves and grows larger, the planet receives increasing amounts of energy, creating a natural laboratory for studying gradual planetary heating over millions of years. The world's fate hangs in delicate balance. It may be engulfed as the star continues to expand, or its orbit might actually move outward as the star loses mass during its evolution. This planet offers astronomers a unique opportunity to observe stellar evolution's effect on planetary systems in real time, watching as changing stellar conditions gradually alter the environment of an orbiting world. The process unfolds over timescales vast by human standards, but rapid in cosmic terms, allowing us to witness planetary fate being decided by stellar aging. Just 281 trillion miles away from us, relatively close in cosmic terms, lies GJ SDIN 1214b, a super-Earth that has sparked intense scientific debate about its true nature. This world, 2.8 times larger than Earth, could be either a water world with a thick steam atmosphere or a small gas planet with a hydrocarbon-rich envelope. The ongoing scientific debate about this planet's composition highlights how much we still have to learn about the variety of worlds that can exist. Its relative proximity makes it an ideal target for detailed atmospheric studies that may finally resolve the mystery of its true nature. The world exists in that fascinating intermediate size range between rocky planets like Earth and gas giants like Neptune, a category of planet that doesn't exist in our solar system but appears to be common throughout the galaxy. This suggests that our solar system may actually be the unusual one, lacking the most common type of planet found orbiting other stars. At 4.3 trillion miles away, HAT P13b demonstrates how planetary systems can be far more dynamically complex than our own. This world, 1. 3 times larger than Jupiter, is heated not only by its star but also by gravitational interactions with a companion planet in the outer system. The two planets engage in a complex orbital dance that causes mutual tidal deformation, generating internal heat through gravitational flexing. This fraternal heating creates thermal conditions that cannot be predicted simply from the planet's distance from its star. The gravitational influence between the worlds fundamentally alters both planets' thermal evolution. This system exemplifies how planets can influence each other across vast distances, creating conditions impossible in single-planet systems and demonstrating the dynamic complexity that can emerge when multiple massive worlds share the same stellar neighborhood. The gravitational choreography between these worlds creates a heating mechanism entirely absent from our own solar system. Located 3.1 trillion miles away, WASP-2b presents us with an atmospheric phenomenon found nowhere in our solar system. A temperature inversion where the atmosphere actually gets hotter with altitude, completely opposite to the normal pattern. Unknown compounds in the planet's upper atmosphere absorb stellar radiation so efficiently that they heat the upper layers more than the lower ones, creating an upside-down thermal structure. This inverted temperature gradient would create atmospheric dynamics, unlike anything we observe on planets in our solar system, with convection patterns and weather systems governed by entirely different physical principles. The mystery of what specific compounds could create such dramatic high-altitude heating continues to puzzle atmospheric scientists, representing one of the many ways that exoplanetary atmospheres operate according to principles we're still struggling to understand. At 13.2 trillion miles distance, the Kepler-11 system showcases one of the most remarkable feats of gravitational architecture in the known universe. 6 planets, ranging from 1.8 to 4.5 times Earth's size, all orbit within a space smaller than Venus's orbit around the Sun. Despite this extreme crowding, the system has remained gravitationally stable for billions of years through a complex chain of orbital resonances. The planets execute a synchronized orbital dance where their periods maintain exact mathematical ratios. One planet completing 2 orbits for every one of another, maintaining delicate gravitational balance. This cosmic choreography prevents collisions and orbital chaos, creating a system where 6 worlds protect each other through precise celestial mechanics. It's a testament to how gravitational forces can create stable configurations even under seemingly impossible conditions. The mathematical precision required for such stability suggests that planetary systems can naturally evolve toward configurations of extraordinary complexity and beauty. Nearly 14 trillion miles away lies Kouro T3b, an object that challenges our very definitions of planets versus stars. With 21 times Jupiter's mass, this world exists right at the boundary between a massive planet and a brown dwarf, a failed star. This object may actually be massive enough to burn deuterium in its core, a nuclear process that would technically classify it as a brown dwarf rather than a planet. Its existence forces astronomers to grapple with fundamental questions about where we draw the line between the most massive possible planets and the smallest possible stars. The ambiguous identity of this world represents the universe's tendency to create objects that don't fit neatly into our human classification schemes, reminding us that cosmic phenomena exist on a continuous spectrum rather than in discrete categories. Whether we call it a planet or a failed star may matter more to human taxonomies than to the physics governing its existence. Finally, at 6 trillion miles away, we encounter WASP-13b, a planet orbiting a star that has already begun its evolution beyond the stable main sequence phase. This world, 1.4 times larger than Jupiter, exists in an environment that changes constantly as its host star evolves, expands, and alters its surface temperature. The planet's slightly elliptical orbit adds seasonal thermal variations to the long-term changes caused by ongoing stellar evolution. This world experiences climate changes on multiple timescales. Short-term variations from its orbital eccentricity, combined with gradual warming, as its star continues to evolve toward the red giant phase. This planet offers a window into the future of our own solar system, showing how planetary conditions change as stars age and evolve, gradually transforming the environments of the worlds that orbit them over cosmic time. In perhaps 5 billion years, the planets of our own solar system will face similar changes as the Sun begins its own journey toward becoming a red giant, fundamentally altering the cosmic neighborhood we call home. As we continue our exploration of the universe's most extraordinary worlds, we encounter systems that challenge our understanding of planetary formation at the smallest scales. The Kepler-42 system, located just 737 trillion miles away, hosts 3 tiny worlds that push the limits of what we can detect across the cosmic void. These 3 planets have radii of just 300, 2,500, and 1 to 800 miles respectively, smaller than Mars and closer in size to our Moon than to Earth. They orbit a red dwarf star that contains only 17% the mass of our Sun, creating a miniature planetary system where all 3 worlds fit comfortably within Mercury's orbit around the Sun. The discovery of these diminutive worlds represents the extreme limits of planetary detection. The planets are so small and their host star so faint that they nearly escape detection entirely, requiring the most sensitive instruments and careful analysis to confirm their existence. Standing on any of these worlds, you would find yourself on a planet smaller than any in our solar system, orbiting a star barely larger than Jupiter, yet still maintaining the complex gravitational relationships that define a planetary system. At 7.8 trillion miles away lies WASP-1b, a world of significant historical importance in exoplanet science. This planet, 4 times larger than Jupiter, was one of the first discoveries made by the Super-WASP project in 2006, helping to establish an entirely new category of inflated gas giants. The planet's surprisingly low density provided the first clear demonstration of how stellar proximity can expand planetary atmospheres far beyond their expected normal size. This discovery helped scientists understand that planets could be puffed up by stellar heating to dimensions that defied theoretical predictions based on mass and composition alone. WASP-1b's discovery marked a turning point in planetary science, establishing the concept of hot Jupiters, gas giants that had somehow migrated inward from their cold birthplaces to orbit scorchingly close to their stars. Their atmospheres expanded like cosmic balloons by the intense stellar heat. Nearly 2 trillion miles away orbits HAT P4b, a world that demonstrates the extraordinary precision possible in modern astronomical observations. This planet, 1.3 times larger than Jupiter, has an orbital period measured with precision down to milliseconds, exactly 3.056 days. What makes this world particularly valuable for science is that it orbits a G0V star nearly identical to our Sun, allowing astronomers to make direct comparisons with the development and characteristics of our own solar system. The extreme precision of its orbital measurements enables scientists to detect subtle gravitational influences that might reveal additional planets or other bodies in the system. This level of timing precision transforms the planet into a cosmic clock, where tiny variations in orbital period can reveal the gravitational tugs of unseen companions, demonstrating how modern astronomy can extract extraordinary amounts of information from the simple measurement of when a planet passes in front of its star. Just 240 trillion miles away lies 55 Cancri b, known as Galileo, a world with profound historical significance as the first planet discovered around a Sun-like star in a multiple-planet system. With 0.84 times Jupiter's mass and an orbital period of 14.6 days, this world represents a bridge between close-orbiting hot planets and more distant cool ones. The 55 Cancri system became an iconic laboratory for studying complex planetary system formation and evolution. The system's multiple worlds, ranging from super-Earths to gas giants, provided astronomers with their first glimpse into how planetary systems more complex than our own might be organized. This planetary system challenged early assumptions about planetary architecture, showing that nature could create configurations far more intricate than the relatively simple structure of our own solar system, where planets are neatly separated by vast distances and follow nearly circular orbits. At a distance of 258 trillion miles lies Upsilon Andromeda b, a planet that holds the distinction of being the first exoplanet discovered orbiting a main sequence star, revolutionizing astronomy when it was found in 1995. With 0.69 Jupiter masses completing an orbit every 4.6 days, this world established the entirely new category of hot Jupiters. The discovery of this planet shattered the prevailing assumption that all planetary systems would resemble our own solar system. Before this discovery, astronomers expected to find gas giants only in cold, distant orbits like those of Jupiter and Saturn. The existence of a Jupiter-mass planet orbiting closer to its star than Mercury does to the Sun forced a complete reimagining of planetary formation and migration processes. This single discovery opened the floodgates to a universe of possibilities, revealing that the cosmos was far more creative in its planetary arrangements than human imagination had dared to suppose. Perhaps no single discovery has had more impact on astronomy than 51 Pegasi b, known as Dimidium, located 298 trillion miles away. This planet, with 0.47 Jupiter masses orbiting every 4. 2 days was the first exoplanet discovered around a Sun-like star in 1995, earning its discoverers the Nobel Prize in Physics. This discovery fundamentally changed humanity's perspective on our place in the universe. Before 1995, we had no direct evidence that planets existed around other stars. The confirmation that worlds orbited beyond our solar system opened the possibility that Earth-like planets, and perhaps life itself, might be common throughout the galaxy. The planet created an entirely new category of worlds that nobody had imagined could exist. A gas giant orbiting closer to its star than Mercury revolutionized planetary science and launched the modern era of exoplanet discovery, transforming the search for worlds beyond our solar system from speculation into hard science. At 119 trillion miles distance lies GJ 5 a world that has generated more scientific controversy than perhaps any other exoplanet discovery. This proposed super-Earth with 3.1 times Earth's mass would orbit in the habitable zone of a red dwarf star if it actually exists. Different research groups have disputed the planet's existence for years, creating a rare case where the astronomical community remained divided about the reality of a discovery. The controversy highlights the challenges inherent in detecting small planets around faint stars, where the signals can be subtle and difficult to distinguish from stellar variability. If GJ 5 does exist, it would represent one of the most potentially habitable worlds known, orbiting at just the right distance for liquid water around a long-lived red dwarf star. The ongoing debate about this world demonstrates how the hunt for potentially habitable planets pushes the limits of detection technology. At 3.1 trillion miles away lies Kepler 186f, a world that represents a milestone in the search for Earth's cosmic twins. With 1.11 Earth radii, this planet was the first Earth-sized world discovered in the habitable zone of its star. Orbiting a red dwarf star every 130 days, this world receives enough energy to potentially maintain liquid water on its surface, while being small enough to likely have a rocky composition similar to Earth. The discovery proved that Earth-sized planets do exist in the temperature range where life as we know it could potentially survive. This world represents our best current example of a planet that might have Earth-like conditions. Solid surfaces, moderate temperatures, and the possibility of liquid water oceans stretching from horizon to horizon. At an extraordinary distance of 2.1 trillion miles lies HD Quent 6906b, a planet that challenges every theory of planetary formation with its impossibly distant orbit. This world, 11 times more massive than Jupiter, orbits 650 times farther from its star than Earth does from the Sun, 16 times more distant than Neptune. The planet takes 15,000 Earth years to complete a single orbit, and its very existence poses profound questions about how such massive worlds can form so far from their stars and remain gravitationally bound. The extreme separation challenges our understanding of both planetary formation processes and long-term orbital stability. No known mechanism can adequately explain how a planet of this mass could form at such a distance or maintain its orbital connection across such vast space. It exists as a cosmic puzzle that continues to confound astronomers. Finally, at 371 trillion miles away, we encounter Beta Pictoris b, a massive world 13 times more massive than Jupiter, orbiting a star still surrounded by the disk of debris from which it formed. The system is only 20 million years old and practically infantile in cosmic terms, allowing us to observe planetary formation processes still actively occurring. This planet actually orbits through the debris disk surrounding its star, potentially influencing the formation of other planets and clearing gaps in the dusty material through gravitational interactions. We are witnessing a planetary system still in the process of assembly, where the final architecture of worlds is still being determined by ongoing gravitational dynamics. Observing Beta Pictoris b is like watching a time-lapse video of planetary system formation, offering insights into the chaotic early phases of planetary development that occurred in our own solar system over 4 billion years ago. As we approach the end of our cosmic journey through these impossible worlds, we encounter perhaps the most remarkable planetary system ever directly observed. The HR 8C7999 system, located 754 trillion miles away, stands unique in astronomical history as the only multi-planet system where we can actually see multiple worlds with our telescopes, rather than detecting them indirectly through their gravitational effects. 4 giant planets, each containing 7 to 10 times the mass of Jupiter, orbit their star at distances ranging from 14 to 68 times Earth's distance from the Sun. These worlds exist in a gravitational ballet of extraordinary complexity, their massive presences creating orbital dynamics that challenge our understanding of long-term planetary system stability. What makes this system truly extraordinary is that we can observe each planet individually, studying their atmospheric properties, temperatures, and compositions through direct imaging. This represents a revolution in planetary science. Instead of inferring planetary characteristics through indirect measurements, astronomers can actually observe these worlds as distinct objects, like studying distant islands through a powerful telescope. The 4 giants create a system architecture unlike anything in our solar neighborhood. Their orbits span distances comparable to those between our Sun and Uranus. Yet each world is far more massive than any planet in our solar system. The gravitational interactions between such massive objects at such distances create a cosmic clockwork of incredible precision and delicate balance. Picture the complexity of this gravitational dance. 4 worlds, each more massive than Jupiter, maintaining stable orbits across distances that would encompass the outer reaches of our solar system. The mathematical precision required to maintain such a configuration over millions of years speaks to the extraordinary organizing power of gravitational forces when they achieve perfect harmony. At a distance of 1 trillion miles lies 2M.07b, a world that represents an entirely different category of planetary system. This planet, with 3 to 10 times Jupiter's mass, was the first planet ever discovered orbiting a brown dwarf, an object that exists in the twilight zone between planets and stars. Brown dwarfs are sometimes called failed stars because they never accumulated enough mass to ignite sustained nuclear fusion in their cores. They glow not with the brilliant fire of stellar fusion, but with the faint warmth of gravitational compression and residual heat from their formation. This creates a system fundamentally different from any planet orbiting a true star. A world circling an object that represents cosmic failure transformed into dim, persistent existence. The planet itself exists at the boundary between supermassive planet and brown dwarf companion, raising profound questions about the fundamental distinction between planets and stellar objects. In this system, the line between parent and child, between star and planet, becomes blurred in ways that challenge our neat astronomical classifications. This exotic system represents a type of cosmic arrangement that has no analog in our solar system, where the star is barely more massive than the largest planets that orbit it. Standing on this world, you would look up at a sun that never quite succeeded in becoming a star. A dim, ruddy glow in an alien sky that speaks to the universe's tendency to create objects that exist in the spaces between our categories. Just 146 trillion miles away lies one of the most controversial objects in astronomical history. Fomalhaut b exists in a state of observational limbo. Scientists continue to debate whether it's actually a planet or merely a cloud of debris created by a massive collision between smaller bodies. If this object is indeed a planet, it follows an orbit so vast that it takes 2,000 Earth years to complete a single circuit around its star. During the entire history of human civilization, from the first agricultural settlements to the present day, this world would have moved through less than 3% of its orbital path. We are observing what might be planetary motion on timescales that dwarf recorded human history. The mystery deepens because the object appears and disappears at different wavelengths of light, behavior more consistent with a dispersing debris cloud than a solid planetary body. At some wavelengths, it blazes forth as a prominent object. At others, it fades to invisibility, as if it were made of cosmic fog rather than solid matter. This observational puzzle has created years of scientific debate about the fundamental nature of what we're seeing. Is it a world cloaked in clouds of dust from its own formation? Is it the aftermath of a catastrophic collision between two planetary bodies? Or is it something else entirely? A phenomenon we don't yet have the knowledge to properly classify. The controversy surrounding Fomalhaut b serves as a reminder that even with our most advanced instruments, the universe can present us with phenomena that resist easy classification. Objects that exist at the very limits of our ability to observe and understand. 3 centuries ago, a mere instant in cosmic time. Astronomers would never have imagined that we could discover planets in old data that had been overlooked during initial analysis. Yet this is precisely what happened with Kepler 1649c, located 1.8 trillion miles away. A world that was hiding in plain sight within the Kepler Space Telescope's archived observations. This planet, with 1.06 times Earth's radius and receiving 75% of the energy our planet receives from the Sun, represents one of the closest analogs to Earth ever discovered. The world orbits in the habitable zone of a red dwarf star, potentially maintaining surface temperatures suitable for liquid water oceans that could persist for billions of years. The discovery of this lost Earth demonstrates that our galaxy may contain many more potentially habitable worlds than we currently know about, hidden within the vast databases of astronomical observations, waiting for more refined analysis techniques to reveal them. Each improvement in data processing methods, each advancement in computational power may uncover additional worlds that have been silently orbiting distant stars, unrecognized in the cosmic census. Think about the profound implications. Somewhere in the archived observations from space telescopes, more Earth-like worlds may be waiting for discovery. Planets where alien sunsets paint foreign skies in unfamiliar colors, worlds where unknown forms of life might be taking their first tentative steps toward complexity, all hidden within data that already exists but hasn't yet been properly analyzed. At 801 trillion miles away lies TOI 7WF one of the most recent additions to our catalog of potentially habitable worlds, this Super-Earth 1. 55 times larger than our planet, was discovered in 2024 and immediately became one of the most promising targets for atmospheric studies with next-generation telescopes. The planet orbits within the most conservative definition of the habitable zone around a red dwarf star, receiving enough energy to maintain liquid water on its surface while avoiding the extreme heating that would boil away any atmosphere. Its recent discovery represents the ongoing revolution in exoplanet detection, where new potentially habitable worlds are being found on an almost routine basis. Red dwarf stars like TOI 715b's host are the most common type of star in our galaxy, making up roughly 3/4 of all stellar objects. If planets like this can harbor life, then habitable worlds might be extraordinarily abundant throughout the cosmos. Scattered around the small, long-lived stars that will continue burning for trillions of years, long after stars like our Sun have exhausted their fuel and died. This world represents hope that life might flourish around the small, stable stars that dominate our galactic neighborhood, creating an abundance of habitable worlds that vastly exceeds what we might find around Sun-like stars. Perhaps no world better demonstrates the power of next-generation space telescopes than K2-18b, located 725 trillion miles away. This sub-Neptune, 2.6 times larger than Earth, has become the focus of intense study after water vapor was definitively confirmed in its atmosphere through spectroscopic analysis. The planet may represent an entirely new category of potentially habitable world. What scientists call a Hycean planet, completely covered by deep oceans beneath a hydrogen-rich atmosphere. Such worlds have no analog in our solar system, but may be extremely common throughout the galaxy, representing vast oceanic environments where life might develop in ways we've never imagined. These ocean worlds could harbor forms of life adapted to exist entirely within global seas, never requiring solid surfaces or shallow waters. Imagine ecosystems that span entire planetary oceans, life forms that have evolved in the perpetual twilight beneath hydrogen skies, alien biology that has never known the interface between land and sea. The James Webb Space Telescope has made K2-18b a priority target in the search for biosignatures, chemical signs of life that might be detectable in the planet's atmosphere. We stand at the threshold of potentially discovering chemical evidence of life on a world orbiting another star, a possibility that seemed like pure science fiction just decades ago. The detection of certain gases in this world's atmosphere, particularly those that would be produced by biological processes, could provide humanity's first confirmation that life exists beyond our solar system. At 287 trillion miles distance lies LHS 1140b, a super-Earth that demonstrates remarkable resilience in what should be a hostile stellar environment. This world, 1.7 times larger than Earth and 6.6 times more massive, maintains its atmosphere despite orbiting an active red dwarf star known for violent flare activity. The planet's high density suggests a rocky composition with a large metallic core, similar to Earth, but scaled up in both size and mass. The stronger gravity would create surface pressures significantly higher than Earth's, potentially allowing liquid water to exist under a broader range of temperatures. Its position well within the conservative habitable zone means it receives the ideal amount of energy to maintain stable liquid water oceans for billions of years. The world has likely achieved the delicate balance necessary for long-term habitability. Enough stellar energy to prevent global freezing, but not so much that runaway greenhouse effects boil away the oceans. This world represents the type of rocky planet that might be capable of supporting complex Earth-like life over geological timescales, combining the stability needed for biological evolution with surface conditions that could remain habitable even as its host star gradually brightens over cosmic time. At our cosmic doorstep, just 25 trillion miles away, lies Proxima Centauri, the closest exoplanet to Earth and perhaps the most important world in our catalog. With 1.17 times Earth's mass, this planet orbits in the habitable zone of Proxima Centauri, the nearest star to our Sun. The planet's extreme proximity makes it the primary target for humanity's first interstellar missions. Various space agencies and private organizations have proposed robotic missions that could reach this world within our lifetimes, potentially providing the first close-up images and detailed analysis of a planet orbiting another star. The journey to Proxima Centauri b would require revolutionary advances in propulsion technology, but the distance is just barely within the realm of possibility for human engineering. Breakthrough initiatives like Breakthrough Starshot have proposed using powerful lasers to accelerate tiny spacecraft to 20% of light speed, reaching the planet in roughly 20 years. Standing on Proxima Centauri b, you would look up at a red dwarf sun smaller and cooler than our own, yet capable of providing the energy needed to warm oceans and drive weather patterns on an alien world. The star would appear larger in the sky than our Sun does from Earth, glowing with a deep red light that would paint the landscape in colors no human has ever seen. This planet represents humanity's first potential destination beyond our solar system, the closest shores of an alien world that we might one day explore in person. At 228 trillion miles away lies perhaps the most extraordinary planetary system discovery of the 21st century. TRAPPIST-1 hosts 7 terrestrial planets, all roughly Earth-sized, with 3 orbiting in the habitable zone where liquid water could exist on their surfaces. All 7 worlds fit within a space smaller than Mercury's orbit around our Sun, yet they maintain stable configurations through an intricate web of gravitational resonances. The planets exist in a state of synchronized orbital motion so precise that it resembles a cosmic music box, each world maintaining exact mathematical relationships with its neighbors. The system represents a natural laboratory for studying habitability around red dwarf stars, the most common type of star in our galaxy. If life can arise and flourish in the TRAPPIST-1 system, it suggests that habitable worlds might be incredibly abundant throughout the cosmos. The TRAPPIST-1 system offers multiple opportunities to study potentially habitable worlds around a single star, providing comparative planetology on a scale impossible in our own solar system. Each of these worlds might represent a different outcome in planetary evolution, some maintaining thick protective atmospheres, others losing them to stellar activity, creating a spectrum of habitability within a single stellar neighborhood. Some worlds might be tidally locked with permanent day and night sides creating extreme temperature gradients. Others might maintain rotation periods that create day-night cycles, seasonal variations, and weather patterns. The system represents 7 different experiments in planetary habitability, all occurring around the same star. Finally, as our journey through these impossible worlds draws to a close, we encounter WASP 189b at 1.9 trillion miles distance, a planet that represents the absolute extreme of hostile planetary conditions. This ultra-hot Jupiter, 1.6 times larger than Jupiter, orbits a blue-white A-type star and reaches surface temperatures of 5,192 degrees Fahrenheit. This world exists in an environment of such extreme ultraviolet radiation that it challenges our understanding of how planetary atmospheres can persist under such bombardment. The planet represents the most hostile planetary environment we've discovered, hotter than some red dwarf stars bombarded by radiation that would instantly sterilize any form of life we can imagine. The blue-white star that WASP 189b orbits represents stellar youth and violence, a massive, short-lived star that burns through its nuclear fuel at a furious rate, emitting torrents of high-energy radiation. The planet exists in this cosmic furnace, somehow maintaining its structure despite being subjected to energy fluxes that would vaporize most materials. WASP 189b serves as a cosmic reminder of the extraordinary range of conditions under which planets can exist. From frozen orphan worlds drifting in interstellar space to blazing gas giants hotter than most stars. From diamond worlds of compressed carbon to gossamer balloons barely held together by gravity. The universe has created a menagerie of worlds that exceeds our wildest imagination. This final world in our journey represents the ultimate extreme. A planet that exists at the very limits of what we might call planetary survival. A world that demonstrates the universe's ability to create conditions so extreme they challenge our understanding of what's physically possible. As you drift off to sleep tonight, remember that above you, scattered across the cosmic dark, spin worlds of liquid diamond, planets where it rains molten glass, and distant suns that warm oceans we have never seen. In the grand theater of the cosmos, Earth is just one player among countless billions, each world a unique experiment in the physics of planetary formation and evolution. And perhaps on some of these distant shores, other minds look up at their alien skies and wonder, as we do, about the magnificent diversity of worlds that dance through the endless night, each one a testament to the creative power of gravity, chemistry, and time working together across the vast scales of cosmic evolution. If you're still awake, it's because the content was really good, so take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.